Yeah, exactly. You can see it in a Friday.
Okay, everybody. Welcome to HAO Colloquium. Our today's speaker is Paul Bryans. It is my great pleasure to introduce Paul Bryans. He's a project scientist at the High Altitude Observatory of NCAR, where he researches the solar atmosphere. He was trained in atomic physics and spectroscopy, gaining his PhD from Strathclyde University on the spectral emission from non-Maxwellian plasmas. He now applies these skills to understanding observations of the solar chromosphere and corona. But he also likes to broaden his horizons as much as possible, and he's conducted research in the fields of supernova remnants, molecular clouds, and comets. He is also increasingly involved in instrumentation projects, including field expeditions to observe solar eclipses, and most recently as the instrument scientist for CMEx. So today he will be speaking on CMEx, Chromospheric Magnetism Explorer.
Okay, thank you, Masumi. So for those of you that are here at HAO, I'm sure you must be sick of hearing about CMEx for now. I know I am. I feel like it's all I've heard about for like the last 3 years. But nonetheless, like people showed up. So I think for most people that are not like intimately involved in the project, you've probably heard it spoken about a lot, but you might not know too much about it. And I think that's because we've been working on it for a few years, but we haven't had like a full-length colloquium yet at HAO. So HAO is the PI institution. Holly's the PI. Alfred Devine is the deputy PI, and Rebecca is the project scientist and instrument scientist. But there's a lot of other people involved here at HAO. Our main partners are at Ball Aerospace, which is just down the road here in Boulder. But then we have a lot of other collaborators and co-Is from different institutions in the US and internationally. So CMEx is a proposal to a NASA SMEX call. So this is, if you're not familiar, this is what NASA calls their small explorers. And it has a cost cap of $150 million. So that puts it in the same class if you're familiar with the Punch mission that was selected a few years ago and is due to launch next year, I think, or IRIS, if you're familiar with IRIS. At the end of last year, we were successful in making the first cut, where NASA chose 4 of the proposals to go forward to what they call a concept study review. So we get 9 months to elaborate on and drill down into the details of your mission concept. So that report is due in August this year. And then a selection will be made for one of those 4 missions to fly. It will fly in 2029. The selection will be made April of 2025 next year. So right now we're in this phase A study where we are developing the design, and as such, things are kind of moving quite quickly. And I think as I go through this talk, you might hear me say quite often, this slide doesn't apply anymore, things have changed. And that's even true for this intro slide, because so we started working with Ball Aerospace. Ball Aerospace doesn't exist anymore. They get bought over by BAE Systems. And this nice graphic we have is wrong as well. That's not what the spacecraft looks like anymore. But we don't have like a nice graphic representation of the new one, so I just pasted it on top there. All right, so let me step back a bit from talking about CMEx, the mission, and talk a little bit about what the motivation for it is first. So our benevolent overlords tell us that the NCAR's mission is science in the service of society. It's no longer enough that we just do fundamental research. We've got to do some sort of actionable science, whatever that means. So as far as the sun is concerned, the biggest societal impact is space weather, eruptive events. And you're all familiar with these sorts of prominence eruptions like you see here, or coronal mass ejections that impact life on Earth. And as 100 years ago, these sorts of events were interesting because they might produce the aurora. These days, as we're getting more reliant on technology that, like GPS, power grids, etc., space weather events are more of an impact on our lives. So active area of research is trying to understand why these things happen with the end goal of being able to predict them. But what is the problem with these images that I've shown so far? That is that all you see here are intensity images. So what they're showing us are the effects of space weather. We can see eruptions, and we can, once they've happened, we can see they've happened. But you can improve your instrumentation to get better spatial resolution, better cadence, but you'll never be able to get the full picture of what's going on if you only look at the intensity of the light. And that's because all these events are driven by the magnetic field on the sun, and you can't measure the magnetic field if you only look at the intensity of the light. So what you want to do instead is look at the polarization of the light to be able to measure the magnetic field. This is, right now, this is done routinely. So this image is from HMI, which measures the magnetic field on the sun 24 hours a day. But this is only in the photosphere. If you want to understand how events are driven in the higher atmosphere of the sun, you have to make some extrapolation of your measurements in the photosphere out into the higher regions of the atmosphere, to get what the magnetic field is doing in the chromosphere and corona. So the photosphere gives you a boundary condition, but the extrapolations are always error prone, let's say. So what we would rather do then is actually measure the magnetic field instead of just relying on extrapolations from the photosphere. So this is a simulation from a Muram code that Matthias run that shows you the photosphere at the bottom, and that's what we can measure today. As you go up into the atmosphere, you can see the change in complexity of the magnetic field. Once you get high enough up in the corona, things are mostly radial and become kind of simple again. But the chromosphere region in between these two is very complex. The atmosphere there is highly stratified. And what we would really like to do is be able to measure the magnetic field in this region that is shaded in orange on this slide.
What's the red lines? Sorry.
All of these, the red lines is the magnetic field, and there's red lines up in the corona. There's kind of blue and white other kind of colored lines closer down to the photosphere. It's all magnetic field. The color, I think, refers to the temperature, maybe. Kind of not really important for the.
Yeah, but I tried this. I wanted to identify which feed lines actually make it up in the corona. So all the blue stuff down there you see that never makes it up. There's only a very small subset of actually feed lines in the photosphere which makes it up in the corona, and those are color coded in red.
Thank you. Okay, so I go back to my problem about wanting to know what the magnetic field is in the chromosphere and the corona. Then here's the solution I should say this is the solution as CMEx intends it. There is another solution, and that's to just send a probe into the sun and measure in situ magnetic fields. But that's not really feasible, at least in the near term. So the CMEx solution to this problem is to measure not only the intensity of spectral lines, but also the polarization and the full Stokes polarization of the line so that we can get the vector magnetic field. But also we don't want just one height in the solar atmosphere. So we don't want just the photosphere. We don't even just want one region of the chromosphere. We would rather sample a range of heights so that we can see how the magnetic field is changing as a function of height. So to do that, we want to choose several spectral lines that sample a range through the atmosphere. And it so happens that the near ultraviolet is the optimal wavelength range to do this. So on the really crappy resolution figure on the left here, shows you the spectral range that CMEx will measure. So from 255 to 281 nanometers. The most well-known of the lines here are the magnesium 2H and K lines, around 280 nanometers. They form high in the chromosphere. They're the highest forming of any of the lines that that form in the chromosphere. But also, there's a whole bunch of other ion lines in this wavelength range that have different opacities and sensitivities to the magnetic field, such that they sample all the way from the photosphere up to the high chromosphere. And that's what you see in the figure on the right. So if I now take this same figure again, but plot the spectral lines as a function of formation height, now you see the magnesium H and K lines form high in the chromosphere, and then there's this whole slew of ion lines that kind of sample all the way through the chromosphere down to the photosphere. Another thing to note is you can see here, so that's the blue line up here is the solar irradiance without the effect of the Earth's atmosphere. And the pink overlaid on top of that is the telluric absorption from the Earth's atmosphere. So all these lines form just shortward of this point here where you cannot view these lines from the Earth. You need to go into space to measure these lines. Okay, so this all kind of sounds great. It kind of sounds, maybe it sounds too easy. In fact, we measure all these lines, we get the magnetic field, and job done. But actually, taking observations of any of these spectral lines and inferring the physical properties of the plasma is not trivial. The way we do it in practice is we start off with some sort of atmospheric model, and then we have model parameters that we can tweak. So the model parameters can be the temperature, the density, the magnetic field strength, and direction. We put them into some radiative transfer code that gives you a radiation output, and then you compare that radiation output with your observations. If they match, then okay, perfect. Those are the model parameters that fit your observations. If they don't match, you kind of go back and just keep iterating until they match well enough. It's more complicated though in the chromosphere because we're in non-LTE, where we have to take into account the statistical equilibrium, atomic excitation, and all of this process is not the best minimum is hard to find for a start. It's an iterative process. You never really know that you've found the correct solution, I guess. And because those solutions depend on the assumptions you make in your model in the first place. And there's just ambiguities inherent to the method here. So people that are more clever than me are working on this for our problems. We've got bunch of postdocs, including David is here, and also Roberto and Rebecca and others. And I don't want to go into the details here, but I've just summarized the way we are going to approach this problem for CMEx. And it depends on the type of region we look at in the atmosphere. Strongly magnetized regions, we would take a different approach to weakly magnetized regions. And then prominences that are viewed off-limb, we have a different approach again. So for strongly magnetized regions, you can assume that the Zeeman-induced signals dominate, and we will assume the weak field approximation there. For weakly magnetized regions, it's more difficult because you have to solve a kind of full non-LTE radiative transfer problem. But thankfully, David Afonso and others at the IAC have developed a code that can do this called TIC. And then for prominences off limb, we have started to work on a PCA-based approach, which Roberto already demonstrated to work for helium 1030 maybe, and now Piyush and him are working on this for the CMEx data. Okay, so I'm sure you agree this sounds great, but you're probably asking, okay, well, why has no one done this already? The answer is it has been done to some extent. There was a clasp sounding rocket which successfully measured a subset of the wavelength range of CMEx. It measured the magnesium H and K lines. The problem, or the limitation, I should say, of a clasp is a sounding rocket, right? So you get 5 minutes of observations. And this was great to demonstrate that this technique could work. I think it helps CMEX's selection prospects that FLASP successfully launched and showed that the measurements they made could infer the magnetic fields. So it showed proof of concept, but it's only 5 minutes of observations. You can't track an active region across the disk for several days, for instance.
Who did the class?
This was a collaboration between the US, Japan, and Europe. So the PI is David McKenzie, who's at Marshall, but there's also strong involvement from the Japanese building some of the hardware, JAXA, and then European involvement was led by the IAC in Tenerife, and they did most of the data analysis, data interpretation. It can also be done on the ground to some extent. So here is some measurements that were made at Sac Peak in the Dunn Solar Telescope. You can measure, and it had been measured, the polarization of the intensity of light and throughout the chromosphere. But if you remember from the figure a couple of slides back, you can't see the CMEx wavelength range from the ground. So if I compare what we can see from the ground to what we potentially will see from CMEx, we have a much finer sampling of the atmosphere because we have more spectral lines there, but also we have the important magnesium H and K lines, which you cannot see from the ground, and they're the highest forming ones, so we'll see higher up in the atmosphere as well. But in addition, on the ground, you can only observe for a few hours a day, depending on seeing conditions and nighttime, etc. So if you're in space, you have the potential to be able to look at the same region of the sun for 24 hours a day over several days to watch an active region, for instance, that has the potential to flare, and watch how it changes and how the magnetic field evolves leading up to the flaring process. To do that from the ground, you need to be very lucky that you're viewing just at the right time that something happens. You don't have the luxury of kind of staying on the same region for a couple of days. Okay, so how will CMEx do this? We're going to be in a sun-synchronous polar orbit. low Earth orbit, so 550 kilometers, such that, so the red line here is the orbit of CMEx, such that we see the sun all the time, 24 hours a day. We have some eclipse season over the winter for 3 months, where there will be some period of eclipses where we every orbit we lose the sun a little bit, but for most of the year we have 24-hour access to the sun. And here's what the instrumentation looks like. We have a sunlight comes in here into a 30 centimeter aperture telescope, hits this mirror, which we use for image stabilization, but also so that we can raster our slit across the sun. And so that light hits a slit and then gets split into 2 different instruments. We have a spectropolarimeter and an imager. If I talk about the spectropolarimeter first, the light passes through the slit, goes through a modulator, a grating, and some beam splitters, and this gives us our polarized light. So this is what we use to observe the Stokes vectors for the light that will eventually allow us to determine the magnetic field. At the same time, the light that does not go through the slit is reflected off the slit jaw and enters the imager. And this imager kind of gives us context for where the slit is looking at a couple of different wavelength bands. So I can talk a little bit more about each of those. So the imager looks like this. It has a field of view of 180 by 180 arc seconds, and it has 2 pass bands, one in the chromosphere centered on the magnesium K line and the other in the photosphere. 0.4 arc seconds spatial resolution, and we have the ability to go down to 2-second cadence. And this is an example of what the imager would see. So this is the chromosphere band, and this is the photospheric band. And I think I said everything else about this already. The spectropolarimeter. This is kind of meant to show the yellow lines are the slit, and we choose a region of this of activity that we're interested in, and we will raster across. So every time the slit moves, that the imager field of view also moves. The slit's centered on the field of view of the imager, and this is showing 240 pointings to cover 120 arc second region, but we can go further than this. We can do 180 by 180 arc second field of view, just using that mirror to steer. If we want to go further than that, we then need to slew the spacecraft, so it takes a little bit longer. And this, I should also say that the spacecraft has the ability to roll to any angle, so we can kind of optimize how our field of view lines up with the solar feature we're interested in. And it measures the spectral range I spoke about earlier. It has a 1 arc second spatial resolution, and this should be updated to a 37,000 spectral resolving power. Here's a little bit more about the kind of optical design of the spectropolarimeter, and we get we split the light into 2 different wavelength bands. We don't cover the entire 255 to 281 wavelength range. There's a kind of gap in between that is less interesting. And to fit this all on the detector, we measure one short wavelength part and one long wavelength part that takes into the magnesium H and K lines. Okay, so I think I wanted to talk a little bit about some specific science objectives, and I've got 4 that we've outlined here. But I think you should look at this as just some ideas of what can be done. I think everyone in this room probably has a different idea of what they would like to use this instrument for, if it exists. So this is to give you an idea of the type of things that can be done. Firstly, we want to look at the magnetic field in and around active regions leading up to the flaring process, measure how, if try and detect the magnetic markers of eruptions. So one theory is that in an active region, as we progress towards a flare, we go from a sheared magnetic arcade configuration to a magnetic flux rope configuration that eventually leads to an eruption. But this has never actually been measured before, and CMEx will allow us to measure the markers of this. So what we see here, the orange lines are the region that CMEx can measure. The bottom orange line is the photosphere. The top orange line is the formation of the magnesium K line. So you can see that the magnesium K line does not always form at the same height in the atmosphere. It varies depending on the conditions. So CMEx can measure everything in between these two orange lines. And so this simulation shows that the magnetic field changes in both in strength and in curvature as a function of height. And that varies depending on if we're in this sheared magnetic arcade formation or magnetic flux rope. So for instance, the field line curvature, shown in blue and red here, stays pretty constant in the magnetic arcade situation, but changes in the flux rope, and also the magnitude of the magnetic field varies with height as well, differently in these two cases. So this shows you, this is a good example of why just measuring one height in the atmosphere cannot solve this problem. If we had only one line, if we only had the magnesium K line, for instance, we wouldn't be able to distinguish between these two situations. So being able to measure throughout the atmosphere and measure a change or otherwise of the magnetic field strength and direction as a function of height, we will be able to see whether we are in one or the other of these configurations, and if we change from one to the other leading up to a flare. And this is also another good example of why you really need to be in space to be able to do this. You could conceivably make these measurements from the ground, but we don't know how long this takes, right? There's different theories of it taking a couple of hours to a fraction of a day for this transition to take place. So if you're on the ground and you're measuring for 2 or 3 hours, you're probably not going to catch this happening. You need to kind of stay on an active region and watch it for a couple of days to be sure of being able to measure this evolution. Another thing we could do is measure rather than the evolution of the magnetic field leading up to a flare, we want to measure the difference pre and post flare. And this would put constraints on flare models, because two kind of open questions right now in the flare community are how much momentum and energy is transported from the corona down to the photosphere during flares, and how does the initial magnetic field configuration affect the evolution and how the flare happens, or if it happens or not. So the figure on the right here shows a simulation of before and after a flare in red and blue, and they look very similar, which kind of shows you the difficulty in making these measurements, but it's within it's within the measurement accuracy of CMEx to measure the difference in the magnetic field configuration before and after.
Paul, can I interrupt?
Yeah.
What kind of cadence does CMEx have to make magnetic map?
It depends how big a region you want to scan over. For an active region, we can run as fast as 3.2 seconds per slit position, and our slit width is half an arc second. So if we want to scan, you've always got trades, right? If you want to scan at the full spatial resolution where you step the slit exactly one slit width, then let's say you wanted to scan 100 arc seconds, it would take that's 200 positions times 3 seconds, right? So we can scan a typical active region in about 20 to 30 minutes. Depends on the size of the active region. You could, if you're only interested in a kind of smaller active region or a subset of it, you can get down to maybe 10 minutes. You also have the ability to kind of step the slit in bigger chunks and lose some spatial resolution for some cadence. So we're designed the observing mode to be as flexible as possible so that we have the ability to change this depending on the kind of science driver. So
Will it change autonomously or will it be a pre-programmed?
it will be programmable it won't be autonomous, no. It will be up to whoever's the science planner for that day to make the decision. And that will be based on previous observations. We might say, this didn't work, like we didn't have the signal to noise we want. We'd rather increase the exposure time here and lose some cadence, or we might decide we want to try and catch some faster moving things. I think what I would say though is I would not view CMEx as something that is going to catch a flaring process, right? It is, you'll see that in the context imager that we have, but really I think the power of CMEx is measuring slow magnetic field changes and the difference in pre and post flare magnetic field, not the impulsive flare event itself. We don't have the cadence to do that. I mean, you could run in a sit and stare mode, right? Where you only see one tiny part of it, but you can have high cadence. Another feature we can look at is prominences off the limb, and this is kind of similar to the previous cases I spoke about, but because the viewing angle is different, we have a different way to interpret the data, and it's in some sense it's easier, but it's because now we don't need to rely on all of those different spectral lines that sample all the different heights of the atmosphere. Now you can just rely on the magnesium K line and take into account the fact that you sample the height of the prominence all the way from its foot point to its top, just with the same spectral line, but because of its viewing angle. So you're looking at side on in this case. And Piyush and Roberto are kind of working on the data interpretation aspects of this right now. And the final science objective I wanted to talk about is a step away from active regions and prominences and look at something called the open flux problem. You remember the figure from Muram I showed earlier, and Matthias made the point of those at the photosphere, there was all the different colored magnetic field lines, blue and red, and different colors were down there, but only the red field lines make it out into the corona. And eventually that's what makes it to the solar wind. Now there's a kind of long-standing open flux problem in the community, and that is if I measure the magnetic flux at the photosphere I get some value, and that's shown in green here. This is a function of time. So this is the total open magnetic flux over the entire solar disk. Then if I send a satellite up to Earth orbit and measure the same magnetic flux getting to the Earth, so 1 AU, the flux is very different from what's measured on the sun. And it's a factor 2 to 5 difference. There's a lot of different theories as to why that should be the case. But one leading theory of why there's that discrepancy is the fact that the flux measured on the sun right now is photospheric flux. So for a start, not all of that flux makes it up into the atmosphere. But an even bigger problem is that most of the open flux is coming from coronal holes. Maybe all of it is coming from coronal holes. Coronal holes are predominantly over the poles, so it's not a good viewing angle for us, right? You're always going to have large errors if you try and infer the magnetic field with that kind of real steep projection effect. So CMEx has the potential to try and improve upon this for a couple of reasons. One is that it does not measure the magnetic field in the photosphere. It measures it higher up in the chromosphere, where a lot of that field that is closed and doesn't make up we're higher up, and more of it will have made it out into the solar wind. But also, we're not relying on Zeeman effect for the polarization. We can use Hanley effect at the viewing angle of near the pole, which does not have the same limitations as the Zeeman effect does. So there is the potential that CMEx can go some way to answering this question if indeed the difference between what's measured in green and red is because the measurement at the sun is just not reliable because we're not really measuring the correct thing. Okay, so that's kind of all I wanted to say about the science we can do from CMEx. I wanted to mention a little bit, in case anyone online is working at NASA and has the decision-making power on this. And that is that, so in 2017, JAXA, NASA, and ESA had a joint report to come up with what should the next generation solar physics mission be. So this was what should the next big flagship solar mission be. And the recommendation out of that was that we should study fundamental physical processes at high spatial and temporal resolution through all temperature regimes in the atmosphere. They envisaged this as one spacecraft doing all of the measurements here. Solar C in its original incarnation was maybe going to do this, but budgets kept getting cut for Solar C, and now it doesn't do all the things that it was originally going to do. But it will do some of the things. And well, let me back up a little bit. So that was a science recommendation. There was an instrument recommendation to meet this science, and that was we want a coronal and transition region spectrograph, a coronal imager, and then also chromospheric and photospheric magnetograms. So EUVST instrument on Solar C measures a real wide range of temperatures on the sun. Spectroscopy, so it's not just intense. It's not just an imager. You can measure temperature and density from it. MUSE, which was the most recently selected MIDEX in heliophysics, is a 35 slit spectrometer that doesn't have the same temperature coverage as Solar C, but it has a much higher cadence because it has 35 slicks and so can scan real fast. So Muse and Solar C together can do the first two parts of this recommendation. But neither Solar C nor Muse have any capability to measure the magnetic field. So CMEx can fill this gap and measure the chromospheric and photospheric magnetic field. It will not do it at the same spatial resolution as was recommended in this report. We have a 1 arcsecond rather than a third of an arcsecond resolution, but we will get some of the way. So I think it's what I would say is it's not. It would CMEx would be so much more powerful. It would be very useful if it flew regardless. But if it flies at the same time as these two other missions, then you can get all of these measurements simultaneously. And I've kind of alluded to that here in the timeline about when these things will launch. So in the end of last year, we were selected for the Phase A study. We will submit that study in August, and in April next year, NASA will select one of these missions to fly. If we're successful, we should launch early in 2029, and Muse and Solar C are already well in their development and are scheduled to launch in 2027 and 2028. So if CMEx is selected, it will potentially fly at the same time as these two other missions. And that's everything. I'll just leave this summary slide up and I can take questions.
Question about the inversion process and coming up with a unique solution. Yeah, I know you've got snapshots in time, but as things evolve, does the temporal evolution allow you to back into a more unique solution? Looking at continuity over time, what the fluid is doing.
Yeah, I mean, I think one well-known ambiguity is there's a kind of 180 degrees like degeneracy in this. So one thing that's often done is if you see a sharp swing from one to the other, you know that or you assume that that's not real, and you kind of you can back it out that way. But yeah, I think the assumption is if you don't expect things to change very quickly over time, maybe that's like a way that you can try and minimize ambiguities there. But I don't know if Rebecca or anyone else wants to comment on that.
The answer is yes. People are developing inversion methods that take into account the temporal continuity. This is at the forefront of what is being done in spectral line inversions in general. It takes massive computing resources because now you have to invert stuff consistently, not just your data cube, but with an extra dimension, which is time. But as what Paul said, you need to make the assumption of some temporal continuity, and if that's not the case, you actually you're making artifacts in the solution by assuming that the time evolution has to be smooth. But people are doing this nowadays, and it's progressing forward. It's out of the scope of what we intend for CMEx, at least what we put in the post. But yeah,
No super in the budget.
Well, what I would say is there's a difference between what's in the proposal and what we will do.
Yeah, absolutely. And what will happen between now and then in terms of development of these methods too.
And it's not just what we will do. I think once any mission flies, the community starts doing whatever they want with the data. So other people find ways to work with it.
Yeah.
Anyone else?
Questions? That figure again, the Murray figure, the red line looks almost vertical. Does that tell us that maybe the extrapolation method may not be too bad, at least for those kind of lines, because it just
That's kind of only good once you get to a certain height, right? Once you get above a certain height, then things are the magnetic field that's assumed open, at least it doesn't connect back to the surface again, is basically radial, but it's also not very interesting anymore. So all of the interesting part is what you see in orange. So
where it changes quite a bit.
John,
Chromospheric bias, yeah, right.
oh, hi.
Is the orange still chromosphere or is the orange corona? Because we know that there are lots of loops in the corona.
Mhm.
So is the orange all just low chromosphere, or are the coronal loops just not represented?
corona loops are just not represented in this figure. I mean, but yeah, but in general, yeah. So I'm not saying the corona's not interesting, right? There's a lots of large extended loops that come back down, of course. Yeah,
Okay, it's just not represented in this particular.
not in this particular snapshot. Yeah.
John, please unmute and ask your question.
Yes, nice talk, Paul. What do you think is the most, what's the biggest challenge on the instrumentation side here for CMEx?
You know, I think it's a little bit counterintuitive. I especially see this as we're coming up for the eclipse, right? We keep telling the public, don't stare at the sun, you'll burn your eyeballs, right? But at the same time, anytime we're trying to view the sun with a scientific telescope, we're photon starved, and it kind of doesn't really make sense, right? But it's even more problematic when you start to go to polarization, because we're trying to measure things that are like 1 part in 10 to the 3. So the biggest challenge from an instrumentation point of view is just the signal to noise. And basically, you want a bigger tail. You want decast in space.
Did somebody say decast in space?
For the context imagery, you have two filters. Are they imaging simultaneously?
Yeah.
On different halves of the detector?
Yes, we've got, so the detector is, we've got 2 different detectors, one for the spectral polarimeter, one for the imager. For simplicity, for the electronics mostly, and we've chosen to use the same detector with the same electronics and everything. So the detector size is driven by the spectral polarimeter needs. It's too big for the imager, right? So we can fit those 2 channels on that detector.
I see. So it's not imaging like half the left half of the slit is one filter, the right half is the other. It's actually 2 images, 2 full images, but going through different filters.
Yes.
Okay, so it has a splitter.
Yeah, it has a just 50-50 beam splitter and then 2 different narrowband filters. Kevin.
What is the telemetry? What kind of telemetry?
We are using Ka band and still a little bit of a trade right now as to how many passes per day, etc. But we think we can get down in the ballpark of 40 gigabytes per day, something like that. We're still kind of ironing out details.
Are there trade-offs in terms of compression or something? You'll be telemetry limited to some extent, or with the slow scaling, it's.
It depends, you know, it depends on what you try to do scientifically. Some objectives, like looking at coronal holes, for instance, for this open flux problem, don't require a lot of telemetry. But if you want to try and do high spatial, high temporal runs on active regions that you think might flare, then those are more they drive more. But we have figured out that even with our most data intensive objective running all day, we can get all the data down. So.
my other question was, to get the coronal magnetic fields, like one common approach is, an extrapolation of the fields measured around photosphere. How is that? Will that still be key technique to get the coronal fields? How will CMEx?
I mean, in some sense, you'll always need to do that if you want global fields, right? Because CMEx does not view the entire disk of the sun. So if you want a global magnetic field model, yes, you're still going to need to extrapolate from some global boundary condition. I say global, I really mean kind of hemisphere, I guess.
Well,
Use some flux transport model to try and fill in the gaps.
An active region scale, do an extrapolation from a measurement, right?
Yeah, we haven't, at least as far as the proposal, we haven't thought about that, but yeah.
For space weather modeling, this is really great because we're actually measuring where it's connected to solar wind. And so for uncertainties in those types of models, taking measurements higher up and then being able to use those is a much better lower boundary condition.
Right, because the chromosphere and the force-free regime, which are definitely not in photosphere, so presumably there would be a great advantage to doing those extrapolations.
Should improve things.
The chromosphere field.
Sorry, don't go ahead.
Director's privilege. You touched on this earlier, but does CMEx have a particular polar science diagnostic or power? Looking at structures around the poles and helping to potentially solve the open flux problem or some other issues of figuring out how the poles connect to the heliospheric current sheet.
Yeah, I think ideally you want some mission that goes out of the ecliptic, right? But in the absence of that, I think CMEx can help fill in some of the gaps there. And I think so. One of the powerful things is that the handling effect is strongest when your viewing angle is kind of at right angles to the, and so it works best near the poles, and it gives you the magnetic field direction, right? So you can do things with the CMEx data that you cannot do with Zeeman-induced polarization from traditional photospheric measurements.
So orbiter will be going out of the ecliptic.
Ish. I mean, it's not going to happen.
But it'll get you some clues. So I mean, do you have? I know this is not your base science, so maybe it's sort of an SEO type thing in the future. But combining orbiter slightly out of the ecliptic photospheric measurements with CMEx, what kind of science does that provide?
Yeah, I think from a proposal point of view, you've always got to be careful what you say you're going to do, right? Because this mission might not exist when you currently fly, right? But in practice, yeah, you want to maximize your science by coordinating observations with whatever's there. So I think orbiter and Parker as well.
Orbiter will maybe getting 10 days worth of data, not very often. I mean, which is good. It's still great.
Yeah.
But certainly there's synergy there.
But when that kind of goes to Kevin's point about the telemetry demands, and I think it's nice that we have found a solution that means that we can run in our high data rate mode and still get all our data down, so that if we want to coordinate with orbiter and run at a high data rate for 10 days, then we can.
Can I ask a very basic question? In your slide about the open flux problem, why wasn't there a open flux problem before 97?
Yeah.
Like, did something happen to one of the instruments?
Why does it match nicely here?
Yeah.
Yeah. It's not just there, right? There's other parts that it matches. I think that's why it remains a problem. If there were just some factor off that was always the same, it might be easier to say, well, we're just undercounting by some amount. But when it varies with time, then it's kind of more tricky to try and figure out what the reasoning is.
Doesn't Soho fly around it?
Soho launched the end of 95, December 95, so.
But also Wind and ACE launched around then as well.
Nick RG has the theory about this. Actually, this is from his, I think it's not, I'm not sure it's published yet, but yeah, it's a great question, especially why at minimum it seems to be more passionate. But, yeah.
Models from online. Yes. 10 minutes.
I have one last. How do you calibrate these instruments on the ground?
What type of calibration?
How do you do like the
Calibration?
spectropolarimetric calibration? How do you shine,
We
photometrically calibrated light onto it?
we have a light bulb, light source. You pass it through some calibration optics that generate known calibration states of light. Then you pass it through in principle, you pass it through your whole system, your telescope and everything to the detector, and then try and back out what you put in. The trouble is that, or not the trouble, but one thing that you have to take into account is that we can only do this on the ground, and then we can't do it again once we're up there. But Hinode SOT did the same thing and has been flying for, I don't know, 15 years or something, maybe more, and it's still performing okay. So we're confident that this approach works.
Does your special light bulb cover the full wavelength range?
Yeah, because that calibration might be wavelength dependent. Right. Yep.
Yeah, just to follow up on that. So is there a way for you to track the transmission of the system over time? I mean, maybe you've got some kind of a diffuser in the door?
No, we don't have any door. What we plan to do is, you're talking about radiometric calibration, right? Just throughput over time. I think the way that other missions do this, like IRIS, for instance, is it measures sun center once a day, every day, and then just does some trend analysis. And they compared the results with source solstice when it existed. It's not up anymore. The kind of the next best irradiance one is it's on the IS. TIS, is that what it's called? Thesis, yeah. Doesn't have the spectral resolution to really help you much. So IRIS has kind of just gone to just looking at trends and a proxy model.
Oh, I see. Thank you.
But we don't. Yeah, you want to kind of measure your throughput degradation over time, but none of the science is really driven by that. This is not like an irradiance mission where you really care about absolute values. So
There is the questions. So let's stand by again 5 minutes.